In this lecture, we will discuss some properties of greatest common divisor. First, we have a theorem, theorem 3.4. This is the first property of GCD. Yet, GCD of A and B equal to D, then GCD of A by D and B by D equal to 1. And the second one is GCD of A and A minus B is equal to D. So let us discuss first one. First one is if the GCD of A and B equal to D, then we have to show that GCD of A by D, B by D equal to 1. Let D dash is equal to the GCD of A by D and B by D. So we have to show that GCD of this is equal to 1, that is we have to show that D dash is equal to 1. Now, since D dash is a common factor of A by D and B by D, because we have D dash is equal to GCD of this, so we have D dash is a common factor of A by D and B by D by the definition of GCD. Since D dash is equal to this, we have D dash is a common factor of A by D and B by D. Therefore, we can write A by D equal to some positive number L into some integer L into D dash, and B by D can be written as some M into D dash for some integers L and M, because D dash is a common factor of this and this. Therefore, we have A equal to L into D dash and B equal to M into D dash. Therefore, D dash is a common factor of both A and B. Therefore, by the definition of, we have the GCD of A comma B is equal to D. Therefore, by this definition we have and we obtain that D dash is also a common factor of A and B. Therefore, by the definition of this GCD we have D dash is less than or equal to D. That means D dash is less than or equal to 1. That is, D dash is a positive integer such that D dash is less than or equal to 1. That means D dash is equal to 1. D dash is equal to, so we proved D dash is equal to 1. That means GCD of A by D comma B by D is equal to 1. That is, if AB equal to D, then A by D and B by D are relatively prime, because from this we get GCD of A by D comma B by D is equal to 1. Now second one, to prove second one is if GCD of A comma B equal to D, then to show that GCD of A comma A minus B equal to D. We suppose that D equal to GCD of A comma B, then we have to show that GCD of A comma A minus B is equal to D itself. That is, we need to prove. We are given that D equal to GCD of A comma B. That means we have D divides both A and D divides B. Okay, that is D is a common factor of A and B. Now we have to show that GCD of A comma A minus B is equal to D. Let's suppose that D dash is equal to A GCD of A comma A minus B. So we have to show that this. So that means we need to show that D equal to D dash. That is our aim now. So we are going to prove like this. We are going to show that D less than or equal to D dash and D dash less than or equal to D. Therefore, from this we get D equal to D dash. That means we will get this. So first we have to show that we are going to show that D less than or equal to D dash. Now, since D is a common divisor of both A and B, because we have D is equal to the GCD of A comma B, therefore we have D is a common divisor of both A and B. Therefore, we have A can be written as A. This is actually from this. Therefore, A equal to MD and B equal to ND for some integers M and N. That is, we can find some integers M and N such that A equal to M into D and B equal to N into D. Because D is a common divisor of A and B. Therefore, A should be a multiple of D and B should be a multiple of D. Therefore, from this we get A minus B is equal to M minus N into D. That means D divides A minus B, and we already know that D divides A, because we have D is a divisor of A. So D divides A, and from this we get D divides A minus B. So we obtain that D divides A and D divides A minus B. That means D is a common divisor of A and A minus B. Therefore, by the definition, D must be less than or equal to A comma A minus B. This is actually GCD of A comma A minus B. Therefore, we already suppose that D dash is the GCD of A minus B. Therefore, by the definition of GCD, we have D should be less than or equal to D dash, because we obtained here that D is a common divisor of both A and A minus B, and we already suppose that D dash is equal to GCD of A comma A minus B. So by the definition of this GCD, we know the D dash is the GCD of A comma A minus B. Therefore, D dash is a factor of A and factor of A minus B. And also, if there is another factor, common factor for A and A minus B, then it should be less than or equal to D dash. So here we obtain that D is a common divisor or common factor for A and A minus B. Therefore, D should be less than or equal to D dash. So we proved this. Now we have to show that D dash is less than or equal to D. We have to show that D dash is less than or equal to D, where we know D is equal to GCD of A comma B. Now also we supposed that D dash is equal to GCD of A comma A minus B. Therefore, D dash is a common factor of A and A minus B. Therefore, we can write A equal to some alpha into D dash, and A minus B is D dash is a factor of A minus B, implies A minus B can be written as some beta into D dash for some integers alpha and beta. Now from these two we get A minus B is nothing but alpha D dash minus beta D dash. So this is equal to A minus B. From this we get B equal to alpha minus beta into D dash. That means D dash is a factor or common divisor of A and B, right? Because we already obtained that D dash is a common divisor of A, and from this we get D dash is a common divisor of B. So D dash is a common divisor of both A and B. Therefore, D dash should be less than or equal to D, because D is a greatest common divisor of A comma B, or GCD of A comma B. Therefore, by the definition of GCD, we have D dash should be less than or equal to D. So we obtain that D less than or equal to D dash and D dash less than or equal to D. Therefore, D equal to D dash. Therefore, we have D equal to D dash. Hence the proof. Next, we have linear combination. Linear combination of the integers. A linear combination of the integers A and B is a sum of multiples of A and B. That is, a sum of the form alpha A plus beta into B, where alpha and beta are integers. So a linear combination of A and B is is a sum of this form alpha A plus beta B, where alpha and beta are integers. For example, consider this: 2 into 3 plus 5 into 7 is a linear combination of 3 and 7. Here we have alpha equal to this, and here we have 3 and 7 are our integers. So this is a linear combination of 3 and 7. Here we have taken 2 equal to alpha and beta equal to 5. Also, this is another linear combination of 3 and 7, taking alpha equal to minus 4 and beta equal to 0. Now we have a theorem, Euler theorem, theorem 3.5. The GCD of positive integers A and B is a linear combination of A and B. That is, if we have two integers, positive integers A and B, then their GCD is actually some alpha into A plus beta into B. That is, GCD of any two positive integers is nothing but the linear combination of that A and B. Right? That is, if we have any two positive integers A and B, then their GCD can be expressed as a linear combination. Right? So to prove this, let S be the set of positive linear combinations of A and B. Set S be the set of positive linear combinations of A and B. That is, S is equal to set of integers like this: MA plus NB, such that MA plus NB is greater than 0 and Mn belongs to Z. That is the set of linear combinations of A and B, such that each of that numbers should be greater than 0. That is, S be the set of positive linear combinations of A and B. First, we are going to show that S has a least element. Since A is greater than 0, we have A can be written as A equal to 1 into A plus 0 into B, where this is alpha and this is beta. That is, we written A as a linear combination of A and B. Okay, therefore, this belongs to A belongs to S, because A can be expressed as a linear combination of both A and B, and it is positive. So this A belongs to S, so S is non-empty. Our aim is to show that GCD of A and B is equal to some alpha A plus beta B. Now, so by the well ordering principle, S has a least positive elementity. We have S as a collection of positive numbers, and we obtain that it is non-empty. That means by well ordering principle we have S has a least positive element and let it be D. Now we are going to show that D equal to the GCD of A and B. We are going to show that least positive element of S is the GCD of A and B. That is we are going to prove now. So since D belongs to S, D has this form, right? Because we have the elements of S are in the form Ma plus Nb, where this is greater than 0. So we obtain that by well ordering principle, we have S as a least element, say D. So D belongs to S. Therefore, D can be expressed as a linear combination of A and B for some integers alpha and B. Now, first we will show D divides A and D divides B. This D divides A and divides B. This is there. First we are going to show this. So by division algorithm, there exist integers Q and R such that A equal to DQ plus R. We know A is a positive integer. So by division algorithm, there exist integers Q and R such that DQ plus R equal to A, where R is lies between 0 and D. That is the reminder. Therefore, from this we get R equal to A minus DQ, and we have D equal to alpha A plus beta B. Replacing that we get A minus alpha A plus beta B into Q. So taking A outside from here, that is we get 1 minus alpha Q into A plus minus beta Q into B. That means this is equal to R. R can be expressed as a linear combination of both A and B, and we obtain that R is greater than 0. So R is greater than or equal to 0. This shows that R is a linear combination of A and B from this. So if R is greater than 0, here we have R is greater than or equal to 0. If R is greater than 0, then clearly R belongs to S, because R is expressed as a linear combination of A and B, and if it is greater than 0, it belongs to S, because S is of this form. It has the elements of this form which are positive. So if R is greater than 0, then R belongs to S. Now since R is less than D, from this, since R is less than D, R is less than the smallest element in S, because we obtained that D is we assumed that D is the smallest positive element in S. So since R is less than D, R is less than the smallest element in S, which is a contradiction. Okay, so therefore R should not be less than D. Therefore R is equal to 0. Therefore A minus DQ equal to 0. That is A equal to DQ. So D divides A. D divides A. So we obtain that D is a factor of A, and in a similar way we can prove D divides B also. Thus D is a common divisor of A and B. Now we are going to show that any positive common divisor D dash of A and B is less than or equal to D. Actually, we obtained that D is a least positive element of S, and the elements of S has this form Ma plus Nb, that is the linear combination of A and B. Now we are going to show that D is equal to GCD of A and B. So we will get GCD of A and B is of this form, some Ma plus Nb. That is we are going to do. So here we obtained that D is a common divisor of A and B. Now we are going to show that any positive common divisor of A and B is less than or equal to D. That is, consider D dash is a common divisor. D dash is a common divisor of A and B. That is, we are considering D dash is a common divisor of A and B. Now we are going to show that D dash divides D dash less than or equal to D. Then we will get D equal to the GCD of A comma B. That is what is we are going to do. So suppose D dash is a common divisor of A and B. Now we get D dash divides A and D dash divides B. Since D dash is a common divisor of A and B, then we get D dash divides A and D dash divides B. This implies D dash divides alpha A plus beta B, because this is by that theorem. If D dash divides A and D dash divides B, then D dash divides any linear combination of A and B. That is we already proved in the previous lectures. So D dash should divides alpha A plus beta B. That means D dash divides D, because we have D equal to alpha A plus beta B. So d dash is less than or equal to d. Since d dash is less than d, d dash is d divides d, we have d dash is less than or equal to d. So from the first part we obtained that d is a common divisor of a and b, and the second part we obtained that if d dash is any common divisor of a and b, then it is less than or equal to d. Therefore we get d equal to greatest common divisor, gcd of a and b. That means we have AB equal to GCD of A comma B is equal to some alpha A plus beta B, because we have D equal to alpha A plus beta D. That is, the GCD of two numbers is a linear combination of that numbers. Now we have a note. The GCD A comma B can always be expressed as a linear combination of A and B. That is, GCD of A comma B is equal to alpha A plus beta B for some integers alpha and beta. In fact, it is the smallest positive such linear combination. That is because we obtained in the previous theorem that this linear combination is D, which is the least such number. That is, we obtained here S has a least positive element D, and it has this form. Okay. Now, if we are given two integers A and B, how to find such linear combinations? One way of finding linear combination is by trial and error. Okay, it can be used if A and B are small. For example, express the GCD of 28 and 12 as a linear combination of 28 and 12. We know the GCD of 28 and 12 is equal to 4 because we have the factors of 12 are, we have 1 into 12, 2 into 6, 3 into 4. So these are the factors of 12. So the greatest factor of 12 is 12, but it does not divide 28. So this is not the GCD. Then the greatest one is 6, but it is also does not divide 28. So this is not GCD. Next one is the greatest factor is 4, but this factor 4 divides 28. So 4 is the greatest common divisor of 28 and 12. So we have this is 4. Now we have to express this 4 as a linear combination of 28 and 12. Okay, that is, we have to find alpha and beta such that 4 equal to alpha into 28 plus beta into 12. So by trial and error, we can get alpha equal to 1 and beta equal to minus 2, because alpha, if alpha equal to 1, we have 1 into 28, that is 28, plus beta equal to minus 2 means minus 2 into 12, that is minus 24. This is nothing but 4. Okay, so we can express this 4, that is the GCD of 28 and 12, as a linear combination of 12 and 24. Now, this linear combination is not unique. That is, the values of alpha and beta in this linear combination is not unique, because in the above example, we can choose alpha equal to minus 5 and beta equal to 12 also. That is, minus 5 into 28 plus 12 into 12 equal to 4 itself. Therefore, 4 can be expressed as a linear combination of 28 and 12 by taking alpha equal to minus 5 and beta equal to 12. And here we are taken alpha equal to 1 and beta equal to minus 2. So, the linear combination of such linear combinations are may not be unique. So the first way of finding the linear combination is by trial and error. Now we have a second way to find the linear combination, that is to find alpha and beta, is by using the table of multiples of A and B and then picking a right combination as the following table. Suppose we are going to express the GCD of 28 and 12 as a linear combination of 28 and 12. Okay, so we need to find this alpha and beta. So here the second way is actually, first we are creating a table of multiples of 28 and 12. So here we have 28 into 1, this is 28 into 2, 28 into 3, 28 into 4, etc. And the another one is 12, the multiples of 12, that is 12, 24, 36, 48, etc. This is multiple of this. So our aim is to express 4. 4 is actually the GCD of 28 and 12. So we have to express 4 as a linear combination of 28 and 12. So here, checking this is 28 and this is 4. 24. Therefore 28 minus 24 is equal to 4. We will get this. So we will get 4 is equal to 28 into 1 plus this is 2 into 12, that is 2 into 12, that is minus 2 into 12. Okay, so we have we obtained this is alpha and minus 2 is beta. Also we obtained this, this is 140 and this is 144, this is 140 and 144, that is 144 minus 140 is equal to 18 4, and we obtained this is nothing but 12 into 12. So this is actually 12 into 12, then minus 28 into 1 2 3 4 5 into 5, this is equal to 4. So we get 4 is actually, we know this is the GCD of 28 and 12. So this can be expressed as a linear combination of 12 and 28, taking alpha equal to 12 and beta equal to minus 5. Okay, so this is the second way.